So I have basically your solution is a workup, which includes 3 or more logic gates, including a NOR, NAND, XOR, or XNOR, one of those. And the first step is to draw the diagram and then implementation view of the diagram. Then create a truth table. Then work up the canonical expressions, a valid logic statement, the HDL file. You run it in the hardware simulator and show a correct rendering of an output for a true case and a false case. And you take screenshots of those. You paste all of those things into a Word document and include the HDL file for your submission later this week. All right, so the assessment, I'm gonna adjust the due time. I think I said that we would give you until Thursday, 1 p.m. to complete the assessment. We wanted to go over the assessment items on Friday. And then we wanted to go ahead and start with Module 5 components, okay? Without further ado, here's what I did. I basically downloaded the diagrams that students emailed me, and I copied and pasted them into a Paint, and then saved them with a letter name so that basically there would be no names. And what I'm going to do is go ahead and show each one at a time. And I will open this with, let's use photos, because that'll make life interesting. Can everybody see the screen?
Yes.
Yes, we can. Yes, we can.
Yes.
Yes.
Okay. So I'm pretty sure this is an AND with a not in the front, so that would be a NAND. A NAND and an and that's an XOR, and that's probably an OR. So I'm thinking if it has a point. So for this artist, one of the things I would share, I like the way that this designer took the multiple splits and the wires from the challenge, logic gate E, right? So you see somebody took the ideas from logic gate E and decided to split this out. So this is going to make for a really interesting logic gate. So if I think what I'm going to need to do is restructure the assignment to allow additional credit for creativity. And I'll do that. I'll add extra rubric criteria for creativity for a variety of different metrics, right? So maybe in your diagram, as you were drawing, adding additional splits is not something that you considered, but we'll add other rubric criteria. Where this designer is concerned, the only thing I would offer, and this is really hard to do because drawing is one of those things depending on what you have to work with, if it's a sheet of paper, if it's a pencil. Because there are 2 inputs here, I'm assuming that this triangle is not a knot. And I'm guessing because there's a point and it's open, this has a curve that has a point, that this is an and that's an or. And that's the only constructive criticism I would offer for this artist is that before they submit their solution, they would redraw it a little bit and try to make it a little more like a high-powered bullet rifle. So what do I mean by high-powered bullet rifle? Well, you have 2 different kinds of bullets. You have handgun bullets, and then you have So bullet shapes, whoops. So can everybody see, yeah, this is a good one right here. Can everybody see this image right here? See if we can get that one in quick. Well, that's not exactly what I wanted to show. It's actually this one. Can everybody see the rounded end here? So these are high powered. So these are high powered. Most of these are high powered rifle bullets. There's a slope, there's a curve, but they come to a point. This is an example of a handgun round. And if this were shorter and it wasn't that's actually a rifle bullet too, but most rifle bullets have the point. And then let's just say 38, right? So when you have handgun bullets, a lot of them are rounded. Well, okay, here's a 380. See how it's rounded? 9mm, 38 special, right? Or 38 super. So when I'm talking about rifle bullets, I mean the or, and when I'm talking about ands, I mean like a 380 auto here. There you go. So a 38 super is like a 38 special, and there's a 380 auto. Those are handguns. And yeah, some of them have hollow points. They're designed for law enforcement to stop bad guys much faster. So a lot of times depending on where you live, some of those are illegal. Hollow points are illegal. But anyway, that's what I mean when I say points. Any questions about that before we go on? Any questions about this diagram? So we have a D that comes in to the top XOR, I think, and then the E splits.
No question, sir. No question.
Yeah. So this person would get additional credit, not just for their creativity, but then there's a second NAND, right? So you have an XOR and you have a NAND. So this is going to be really cool to see what it does. Would anyone care to guess or predict what the behavior is going to be? Because you have ORs on this side, and then you have an AND and a NAND and an XOR. I guess we'll wait and see. All right, let's take the next one. I'm supposed to be able to just move to the next. What's going on here? No, that's not what I wanted. Let's take a look at B. And let's open with, yeah, let's go to photos again. Okay. Wow. Okay, so again, this would score additional credit. This designer included more than just 3 logic gates and included forks, splits, right? I believe that's the XOR. And then we have 2 ands and 2 ors. Very nice. And that's easy to follow. So we have A, B, and C inputs and at the top of the XOR, and then B forks down here into the bottom of OR and into the bottom of the XOR and then into the top of the AND. And then C does something like this too. So I like the shapes. So we're not dealing with a triangle where you might think or get confused so the reason that a triangle is only troublesome is that when the diagrams get really small and there's lots of logic gates, it's harder to pick up that there's two inputs for a triangle, and people see the triangle and they think, oh, okay, that's a knot. The shape of the curve to the point is good. Curve, I like this. The only thing I could offer, and this is really hard because I'm having to search here. It might be this right here. If the line was run up and then looped on top and then continued, it would look like this wire is laid on top of the C, but that's a pretty trivial thing. The fact that there's a distinct dot means that's an interface. It's a junction, and they're two separate wires. The dot's really pronounced, so it's not like you get very confused. This is really good attention to detail. I like this. Does anyone have any questions about this logic gate before we continue?
No question.
Okay. I like the fact that the ands and the ors are arranged kind of in parallel. So in other designs, you see like the ors over here and the ands out here, or the ands over here and then the ors out there. But you see an early and an early or, and then you see a later and a later or. So that's going to make life interesting for the behavior of this thing. It's really yeah, I like that. Anyway, just thought I would, there's my arrow. See, I want to go to the next one. Okay. Oh yeah, once again, we have 5 internal logic gates, and this person is not shy at all about mixing it up. So we've got XOR, XOR, and a NAND, and a NOR. Holy cats. I think this...
Yeah, Dr. Kentop, yeah, I was kind of, I wanted a little,
You wanted a challenge.
I wanted to challenge it a little bit.
Well, you certainly have it. So you have one lonely little... Aaron, I love this. You have one lonely little OR down on the bottom here. But wow. Yeah. Okay. Yeah, this keeps getting better and better. So you have the XOR, you have the no. Oh, that's an XNOR, isn't it? With that curve back there.
Yes, it is.
Yeah, XNOR, XOR, NAND, and NOR. Wow, you flipped it. Okay. So this is not a junction, correct? This is the B line hopping over the C right here?
Yes.
Okay. So the only thing I could offer this designer in the way of constructive feedback is I would make the dots where they're forking a little more prominent. Round dot, round dot, round dot. And then just as we did with the previous designer, when you have to cross over a wire, just stop short, loop over, and then continue. So it visually looks like they're laid on top of each other. That's it. But otherwise, yeah. Yeah, I'm gonna have to change the scale of the rubric for this, for additional credit for everybody. I'm impressed with what I've seen on every diagram to this point. So, oh yeah. So, all right, so let's talk about the fact that we're used to using W1 and W2 and W3 for the labels for the wire. And I'm excited about this design because somebody's using different labels. K could be connector, I'm guessing, maybe. But I'm excited that somebody's going to attempt different letter arrangement, right? So this isn't just like the series of letters in order, right? Like ABC or XYZ. So you see, this is kind of mixed up here. You have Y and A and J. This would be off the charts for complexity as well. For all of those reasons, somebody is including a lot of variability. I need to pause for just a moment here, if you don't mind. Okay, thank you for holding. Once again, a very rich array of inputs. So how many possible combinations of outputs? See this is going to be amazing here. So how all right, let's back up. To this point, we've seen 3 inputs. How large is our truth table with a 5 input complex logic gate? Anyone?
Five inputs would be 32.
32 inputs is 32 possible combinations is correct. 5 inputs, so we have GH, I think, and then that might be YA. So this will make life interesting with the HDL because you're going to have a lot more variety on the, instead of reusing so many letters. So all the other previous diagrams, there were forks in the wire, so the inputs were reused. So that kept the truth table combinations down quite a bit. But the use of extra wires here and then labeling them K instead of W, it's going to be really interesting to see how the HDL accepts that. I don't think there should be a problem using K1 instead of W1 or K2 or K3. So a lot of creativity here. I'm very encouraged by this. This is a NAND and an XNOR and an OR. So I would like to ask someone, what do you call this combination right here? What's another name for these 2 logic gates?
NAND.
NAND is correct. So this NAND and this AND and NOT is actually the same, it's functionally the same. Now, I can think of all sorts of reasons why you would want to, what's interesting about this is there are cases where you want to separate the output and then you want to treat it separately. It all, you know, logic scenarios vary as richly as your imagination. So there could be cases where you want to see what the initial output is, and then you want to throw the NOT on to flip it, because NOT is going to flip it. And there could be cases where it's desirable to work the initial output as opposed to the final output. And I'm just thinking that that's one reason why you would separate or isolate those 2 functions. So, and that's got me thinking or curious about the scenario for this, but this shows, yeah, I haven't seen a single diagram yet that doesn't reflect a great deal of thought and creativity. So once again, anyone have any questions on this diagram before we move on? Okay. Oh, so this is so cool. So The previous diagram flipped it and had 5 inputs. Every one of the diagrams before that had 3 with forks. And this one splits the difference. So the B input is the bottom input for the top and the top input for the OR, and the C is split. So, and there's 3 and then 2 and then 1. Oh, that's elegant. Except that that's a NOR and that's a NAND, I think. Pretty sure because that's a NOT. So that would be a NOR and a NAND. That would be the only constructive criticism I would offer for this designer, is that if you put OR and then you put the dot, people are supposed to know better. But if you want to be consistent with the symbol and the label, you'd probably want to say NOR and NAND. But other than that, I'm impressed by how neat this is. And I mean, this is the kind of thing that would be really easy to follow. So this is you know, I mean, everybody draws differently, don't get me wrong, and some of us are better at drawing than others, but I like the consistency here. It's very uniform. And again, it's very easy to follow. So let's see, how many different wires do we have? Oh, I almost missed this. We have a secondary fork coming out of the NOR, and then it splits to go into and. That's the first time I've seen a wire split past the first layer. Cool. Wow. Yeah. So how large is the truth table for this one? A, B, C, and D.
16 inputs.
16 possibilities with the 4 inputs, yes. And so you'd have a W1, a W2, which would also be the W2 here. So the tricky part for this, when this wire is split, so the external C is split. So when you're doing your HDL, that big C is going to be in both of those statements for this OR and this OR. Same with the B, it splits. So the large B is going to be in the HDL statements and the parts statement for this and this OR. Everybody knows what I mean when I say that, yes? Kind of, sort of? Like if you had little a, little b, little a, little b.
Kind of.
Kind of, okay. This one is tricky because the split's occurring on the second layer. So you have W1, you would leave this W2 and it would feed into the little b for the inside b of this second and it would, W2 would also be the first input here, that little a input for here on the HDL statement for this and, I'm sorry, this NAND. So the term W2 would apply both in this case on the lower input and this case on the upper input. And that's the only thing that would be tricky as far as the HDL. So whoever did this, I hope you're hearing what I'm saying. Then you'd have W3 down here, you'd have W4 and W5. Very nice. That, I can't wait to see this. I mean, I can't wait to see the truth table. I mean, I have never seen the variety I'm seeing today. The truth tables. Is everybody interested in like sending a truth table before the start of class tomorrow, maybe? What do you think?
Tomorrow.
Yes, that would be good.
We wouldn't have class.
Oh
Oh
yeah.
right, we don't have class.
Yeah, no class.
Oh, and we're going over the assessment items on Friday. You can email me your truth tables and I'll respond back. Because I know who these diagrams belong to. And interestingly enough, so this is the kind of thing you would see at NASA for the circuit board of a like a lunar landing module or something. This is cool. All right, so we have NAND 1, NAND 2, NAND 3. We have 3 NANDs in a row. That's the first time I've ever seen a combination logic gate, a higher level logic gate on a whole tier like that. So I'm loving this again. That XOR is in an interesting place. So that's going to take inputs from the 2 NANDs, and it's going to identify the differences there and then pass those on to the OR. You know, the more into the weeds you get, the harder it is to predict the behavior of it, and that's where the truth tables get to be so important. Very clear outlines, very pronounced forks, and you know the wire is they're not connected, they're laid on top of each other. So yeah, this is really, and all the wires are labeled. This is very, very nice diagram. There's 3 inputs, but what's inside really rocks here. So good job. Any questions about this logic gate before we continue?
No question.
Okay. So it's obvious there are points. I'm looking at ORs or NORs, right? So there's the NOR. So for this designer, I would say if you just write NOR in here. For anybody to this point that hasn't added like wire W1, W2, W3, it might be good to do that on any diagrams we've seen to this point. This is also rich. So this is like the same thing we were just talking about. 3 of the most complex, the NOR, the NAND, I'm sorry, the NAND, the NOR, and the XOR on the first layer, and then you have a second tier out here with the regular, or the, you know, the standard logic gates. So that's the first time this is the second time. So previous one where we had a full slate and the first layer of complex logic gates, now we have the NAND, the NOR, and the XOR. Wow. And then the OR, the AND and the OR. So once again, the truth table is the only way, the only real way to work this. And you know, every one of the truth tables that we're seeing here are going to take a step-by-step process, right? So the goal of practicing a walkthrough for logical actions, I couldn't ask for better with what all of you have done, because as you're doing your truth tables, you're going to have to retrace the same steps you did for logic gate E, the challenge. You're going to have to take A, and then you're going to have to say, okay, B comes in, and you're looking at your truth table, and you get the C input. You say, okay, B comes in here, so this NOR, you're going to have to consider the variations for each case. This is the first time, oh my gosh, I just saw this. I've never seen this before either. I've seen splits, but I've never seen a 3-way split where the A input comes all the way down into the bottom.
Mhm.
I want to change lesser right here.
That is amazing. The A comes down, hops over the B, hops over the C. I got an A input right here.
USB tray.
And then I
Here you
have
go, my
B
bad.
and C. So, wow. That, I'm speechless. I have never seen, that's like 3-dimensional. Okay, so I think there's something about a 3D electronics, one of the videos that I put out there. And this is how you make that happening. What am I saying? Well, three-dimensionally speaking, you can take this logic gate and rotate it up into the y-axis. So you have, well, I'm sorry, z-axis. So normally everybody lays this out flat in 2 dimensions. When you start putting these wires and you fork in creative and elegant ways, the only way to solve that problem is to take this logic gate and put it on a second level, like second floor. So this would be like, all these logic gates would be like the first floor. Everybody got me? Does that make sense? So
Yeah, that makes sense.
yeah, if we're laying flat, right? And then let's say that, you know, we don't want to overlay wire too much, right? So one approach would be to take this and then rotate it up into the z-axis, right? So it's like on a second floor, and this A fork is actually like coming up instead of over. So that would, okay, I'm not going to ask anybody to draw 3D diagrams, like, and I'll just exhale it at this point. But I'm excited about this. This is the first time I've seen somebody hop from the A and split the A and run all the way down to the bottom. And at the same time, split like B and C. Wow. And then you have the NAND and the NOR. I mean, I saw that. I'm like, well, okay, that's a different way to shake it up. But that really takes it to a whole nother level. Any questions about this one before we go on to the next one?
No question.
Oh my gosh. I know somebody didn't go out onto the internet and get like free software where you draw your own logic gate stuff. Did somebody actually do this? This is like Christmas. Christmas came early this year. Holy buckets. Oh my gosh.
I used free software.
Yeah. Okay, so who are we speaking with?
Robert.
Robert. Mr. LaWare. We have to talk. All right. So the free, all right, so this, all right, so let's talk, and just remind me that we need to talk about the T and the U and this piece right here, okay?
Right. Yeah, I realized that. Made a mistake.
All right, so you got like an input, but then it's another input right here. So what we want to do is, I mean, you could fork off of this into the OR, maybe? I don't know. But yeah, but that would likely happen while you're noodling. All right, so let's be kind to Robert here. So when you did this free software, a lot of times when you're like moving the elements around, this has happened to me when you're like sliding stuff around on the screen. What happens is that if you slide the wires a certain way, they'll like detach and rejoin and junk. I don't know if I'm making any sense, but
Yeah.
so sometimes if you grab a wire or a connector and you slide it, depending on whether or not it remains attached or it breaks loose, it all depends on the software. Everybody's mileage varies. Robert, would you be willing to share with the class what the free software was you're using?
Yeah, it's draw.io.
Draw.io. And were you the one that said that you do some of this on the job too?
Yeah. Yeah.
Yeah. Okay. Yeah. So draw.io. Is that like a Google Play app or an iPhone app or just off the internet?
No, it's off the internet.
And is it it's like a Python thing or just a?
No, it's pretty much for any kind of design applications, whether it be for UMLs or engineering, any kind of designs you want to do. So I just searched for logic gates.
Wow.
And it got the symbols and the components.
Wow. Okay, so I don't know if you know this, but I think students. All right, so I'm gonna flip back for a second. there's a program that Microsoft has called Visio, and they may have a logic gate component. It's pretty expensive though, and I think it's available as a part of Office 365 or out on the Microsoft downloads. Used to be, you could get Visio. But it's nice to know that there's open source. Thank you. Yeah. So, all right. So the only thing I would offer in terms of constructive criticism is that you need to do something with the T input down here in the lower part of NOR. Okay? Because by looping the two inputs here and there, that's going to get wonky. Yeah. I mean, HDL, and when you run your HDL, if you left it like this and did the HDL like that, it would throw a red line at you. You'd have some kind of error. I'm not sure. But you can get creative with inputs and forking inputs. So you could run the T out and fork it, bring it into here, and then bring it into there as well. That's a quick solution. You have some options. Yeah. Okay. Any questions before we go on to the next one? Okay. So we have P, Q, and R. And we have a differentially apply. I like this. All right. So once again, we all vary in our abilities to draw, but it's very obvious to see what we're dealing with here. So we have an AND and an OR. We have the NAND, but we have a differentially applied NOT coming into the bottom input of the AND. And I love that, because in the advanced solutions I've seen in the 5 years I've been here, believe it or not, I have never seen anyone take a simple NAND, simple NOT, and differentially change the input for a logic gate, except for the earlier in the course. So earlier in the course, when we show people the differential, the first logic gate solution that we have, it's like people forget the simple but elegant creative measures. I don't know if I'm making sense here, but people get they get on in the later chapters, and then they forget, oh yeah, I can differentially apply a NOT, and that can change the behavior of the AND dramatically, because I'm flipping the input of an AND, and everyone knows that ANDs are very picky, they're very restrictive. So that kind of mixes this up. Not the same as a NAND, right? Because with a NAND, you have the AND and the NOTs changing everything universally coming out of there. So that's going to be interesting to see also. And yeah, very clean design. So W1, W2, very easy to follow. Simple but elegant. And so typically when you have complex logic gates that are limited in the number of internal logic gates, right? We have 4 here, a NOT, an AND, an OR, and a NAND. It's easier to try to predict what's going to happen. So ANDs are normally going to be false unless both inputs are true. So the P and the Q would be true. The P is the input for the OR, so that hops down. Here's another case. Oh, look at this. This is the second case where somebody's taken the first input and forked it down to the lower logic gate.
Third case.
Yeah. Don't be deceived when you see a simple but elegant diagram, because there could be a lot of creativity in it. So here's a case where the top input is forked, and then it hops over, I believe. It's not joined. It's not a splice, but hops over. So it'd be good to have a little hump there, but okay, comes into the OR. Yeah. Yeah. So there's a lot of creativity in a small package. Awesome. Here we go. Okay. And this was done with a tablet and a stylus. Could be on a smartphone. That's tough. And to do it by hand, that's really hard. All of you have seen my early diagrams too. So whoever did this, my hat's off to you for being courageous. So you have this A, and then it's obviously a NOR. So you've labeled these, and that helps. That's an AND, an OR. We have the splits, the OR and the AND. So this gets the job done. This would be creative because of the splits and because there's more than 3 logic gates, right? So on the creativity scale, this is really up there as well. With the NOR, we're going to see. So it's interesting. NORs don't behave quite like ANDs. Well, NORs behave kind of like ANDs. Remember the behavior sheet, right? So ANDs are always false unless the inputs are true. NORs are always, is it NORs are always false unless the inputs are 1? I forget. Yeah, something like that. Anyway, the point is that you have
Hey,
this,
I'm here now.
yeah. Okay, glad you could join us. So we have these 2. Now let me grab this real quick. Yeah. There we go. So we have these 2 nearly identical in behavior, but slightly different kinds of logic gates. And that's gonna, I'm curious to see what this does on the truth table. What did we say? I don't want to misrepresent here. I think it was previous one, 3. A canonical summary, right? And is always, you know, I told you, and NOR is similar to AND, right? But it's not. So AND is always 0 unless all inputs are 1. NOR is always 0 unless all inputs are 0. So there's only one case where it's true, and there's only one case where it's true. And they're side by side. That's going to be interesting. I got to see what happens there. So the outputs there hit an and the output here hits the OR. Then you have this combination OR. You have like this 3 input OR. Yeah, this would be kind of like the Democrats sneaking in through the basement to win the election. I probably shouldn't have said that. I'm just thinking, I mean, oh my gosh, how good it's been the last few days. You know, I don't know how long the euphoria is going to last, but I'm enjoying it. But yeah, there you go. Yeah, the ORs. So the ORs are all about inclusion and, you know, inputs. Most of the inputs for ORs are going to come out true, right? So ANDs are exclusive, ORs are inclusive. And this is an interesting combination here. And just like the diagram earlier in our session, I said, hey, you have a set of logic gates on the first level, and then you repeat it the next layer out. So you have an AND OR and an AND OR. So this is going to be an interesting one too. Don't you love the variety and the thought and that, you know, the coolest part to me is people do this and they start combining the logical functions together, and the world has changed. You know, every year they invent new digital components that do bigger, badder, faster, better, because people are willing to get creative. You know, 5G is coming. It's going to revolutionize cellular service, so we think. A lot of challenges with the 5G framework of standards. There's going to be challenges in terms of the hardware. So the hardware is going to work differently. And that has a lot to do with the networking protocols and the frequencies. That's something that'll come up in CSC 243. Not to waste the opportunity for a shameless plug, but in case any of you have not yet taken CSC 243, Digital Communications and Networking, in the spring, if you schedule a time with your advisor and get your PIN code, you can lock down a seat in the digital networking, well, the Digital Communications and Network course in spring, if you're with us for computer science or you're with us for the ACS Tech program. And yes, we kind of circle back around and we get into XOR and we get into AND when we talk about subnet mask and we talk about cryptography and encryption on a network level. It's very cool stuff. And let me tell you what we might have, given the variety of creative combinations here. We may have the basis for a new chip that encrypts in a different algorithm. So encryption is one of those things. Every time so XOR is one of those logic gates that's used for encryption algorithms, but XOR is not the only one. It all has to do with structure. So one of the coolness factors of creating a new design and working the truth table is to find out if the outputs are consistent. So you have a set of inputs and you have a defined output. And if you can take a set of inputs that mean something and always get a scrambled egg the same way on the outside, I'm oversimplifying here. And then on the other side, you have the reverse, right? You take the special scrambled egg that's always scrambled that special way, you feed it back through the process, kind of like, oh, what two logic gates are we covering this module that are the reverse effects of each other? Hello? Did I stump you? Well, actually, there's two pairs. There's two sets of logic gates that are the reverse of the other, mirror reflections of each other.
Nans and ands, ahs and ahs.
Ands and nands are functionally, yes. All right, I take my statement back. You've just corrected me. Thank you. There are more, well, all right. So when I was talking about this, let me clarify. So your statement is accurate and it is correct. If you're considering previous logic gates, the simple basic logic gates like and or and nor. So you are correct. I was referring to the logic gates that we're focusing on. XOR and XNOR are correct, right? So XOR and XNOR are mirror images of each other. Can anybody think of two other logic gates that are like the reverse function of each other?
Or NAND.
Or and NAND are close. They're similar in being complementaries. They're similar. I can
XO.
O and XO? XOR? Or an XOR? Not quite. Let's look at, let me get back into here. So here's our final version of the, here are the, oh, I should have said digital. I know why you didn't get it. I should have said digital components or logic gates. My bad. Among the digital components or complex logic gates that we are covering in this module, we said that XOR and XNOR are functional mirrors of each other, right? This one does one, they do reverses the other. Are there any other like that that we have done? How about this? Mux and demux. So, all right, so let me finish the thought, just so we don't get into trouble here. In the variety of designs we have seen today, we could have the makings of a cryptographic, a hardware-based cryptographic solution, where the output is predictably the same with a variety of ones and zeros being input, and then the flip design would render the decryption. So encryption, decryption. Is what I'm saying kind of sort of making sense? Kind of sort of?
Yes.
Yeah, yeah. Hardware-based encryption is usually very efficient and very fast, and it's going to be a huge factor in cybersecurity in the next 20 years because the software-based methods of protection and encryption are, well, they're getting hacked. And their performance is not up to speed for high volume network traffic, and that's a problem. So this is an area that's really rich when it comes to predicting the outputs of digital designs. Outstanding, everyone. Does anyone have any questions for me about our expectations? So we're not having class tomorrow. It's a day off. Everybody enjoy the day. I am a veteran. It'll be the first time I've enjoyed Veterans Day since I've been out of the service, actually. I've had to work every Veterans Day except for tomorrow. So I'm gonna raise a toast to my brothers and sisters in arms.
Yeah.
Yeah.
So
Yeah,
Yeah.
interesting drawings I find.
also, one more question. We're gonna be
Yeah.
making a table off our drawings, right?
Yes, that's a great question. You are making, the next step is to take your drawing and go ahead and build the table that goes with it. And you can email that to me. I'll just send an email like I did before. And then that can be in process between now and Friday. But remember, you need to take your first attempt of your module 4 assessment before our class on Friday. I cannot postpone it. We do have to bring it, have to review the item assessments on Friday, okay?
Sounds good.
All right. We're gonna stop the recording. You all have a great holiday tomorrow, and we'll see you Friday.
Yeah, you too, man.
All right.
Okay, okay, you too.